before we get started? Okay, so I sent out a message earlier about several things. Just want to make sure we're touched on all of these. I put your extra practice quiz on Moodle for Quiz Friday, on this Friday. We'll probably just, gosh, I guess just a couple more. And then the concept, I put the final concept coach assignments. If you've been doing that, we're doing our final 3 sections are 27.1, 0.3, and 0.4. That's covering the stuff that we're doing now in Chapter 8. And then I've also posted your current standing. Oh, let me bring this back up. I'm sorry. You've posted your current standing. So I actually relaxed it a little bit. I'd said 80% complete in order to get any credit at all, but I relaxed it to 70%. So if you get up to 70% correct, then you can earn up to 10 extra credit points. And then I relaxed these criteria a little bit. If you get more than 70% correct, so of the 70% that you do, if you get 70% correct, then you'll get 10 extra credit points. If you get less than 70 but more than 40, then you get 7 extra credit points. And if you get less than 40% correct of those that you complete, then you'll get 3 points. So only a few of you actually have credit right now for it, but you have up until the last day of class if you want to do that reading. I think that on Concept Coach you can see which sections you've completed. Am I correct about that? That is correct. Okay, I think that's correct. If it's not, shoot me an email and I can send you the itemized stuff and let you know where you haven't done or whatever.
These points are added to a test.
They're added to a test. They go all into one big pot. So I don't want to mislead you. 10 points, it seems like a lot, but we have 600 points total. So it's really only about, what's 10 divided by 600? Really tell me. Okay, it's 1.5 percentage points. That's not shabby, actually. That's pretty decent. Are there 600 and 650 in this class? What's that? I think it is 600. Okay, so roughly about a percentage point. But if that's you, it's good to have that percentage point. Between a B and an A, it's kind of nice. Okay, so we'll have one other opportunity for extra credit, and that will be that general education assessment. You'll take it sort of before or after your final at the end of the semester. Nothing to do to prepare for it. Prepare for your final and you'll be ready for that assessment. All right, let's see. And we won't have a help session on Thursday. I'm sorry, we'll have a help session probably next week or so. Any questions, Joe? All right, let me just remind you while we're thinking about it. Look at the syllabus right quick. Our next exam is on May 2nd, so we're right here on the 13th. So that means we have 7 more class days until May 2nd. And we'll have evals next week, so that'll kind of need a little bit. But we'll have 7 more class days. We really only have this chapter and then 1 more chapter. I think I had not promised, but I said that we might have an off day, and so we'll probably have an off day during those next 7 class days. I'll let you know. I want to get into this next chapter and make sure that we'll have plenty of time to finish it. But it's the chapter on sound. Normally, I would have that in the first semester, but it's a new chapter, and it's important for y'all to get. It has health applications. It's on the MCAT. It's all that jazz. So. Okie dokie. How y'all feeling today? Ready to get started? Now let's do the concept test. We can do a few of these from in the back of your book. This is similar to the one we did before. Here I have waves A and B, and they're superposed, so they're added together. And which of these is the resultant wave? If I add waves A and B, which of those represents the resulting wave? All right, we'll stop, say, at 105, 105. Just guess if you're not sure. It's 5 more seconds. Listen, I just want to tell y'all, like, my department head, he asked me this morning, he's like, so, how many people did you have come to class today? And like, in this class, practically everybody's here. There's just a handful of you missing. And that's really awesome. Y'all are, never tell y'all this? Like, I know y'all think I'm just making this up, but y'all are like the best students that I've had. As a class overall. Y'all think I'm lying? You think I tell that to everybody? I don't, actually. What? Okay, C is the right answer. I add this up. So when I add these two waves up, these two segments give me this. These two segments give me this. And then when I add this up, this segment gives me right here. These two parts add up, like the whales, like that, to make a really big wave. And then these two parts add up to give me that. Every time I do this slide, I always think that the thing is like giving me, you know, the finger. Y'all know what I'm talking about? The middle finger. I shouldn't do that, it's kind of vulgar. Okay, these two waves are what? Are they out of phase by 180, 90, 45, 360, or are they in phase? Remember, how much is it offset? By how many wavelengths is it offset? And that will tell you by how much is it out of phase. All right, we'll stop at 1 minute. 1 minute. A, B is right. That's awesome. I didn't expect that. Well, okay. You can, if they're off by a quarter wavelength, which is what they are here. They're off by 1/4 wavelength. Then they're out of phase by 90 degrees. But you can just sort of, if you're not sure if this is off by a quarter wavelength or not, you can eliminate a lot of these other answers. Because if they're out of phase by 180, option A, that would look like this, where you have complete destructive interference. If they're out of phase by 45, well, you know, I'm not going to show you. That would be out by 1/8 of a wavelength. I'm not going to show you that. If they're out by 360, that means that they're going to look like this, where you get constructive interference. So this would be like part D. And then if they're in phase for option E, they'll look like this. Notice that D and E are very similar, right? You still get constructive interference, except on D, you are shifted over by a full wavelength. Okay? All right, so the answer then is B, 90 degrees. You might see this in your calculus class. We're not going to do this here, but you could see it in your calculus class by radians, where you'd have 2 pi radians. Don't write this down, but 2 pi radians, pi radians, or pi over 2 phase shift. You might have seen that in your calculus class, but we'll talk about it in terms of degrees. Okay, 2 light sources emit waves of wavelength of 1 meter, which are in phase. The 2 waves from these sources meet at a distant point. Wave 1 traveled 2 meters, and wave 2 traveled 3 meters. When the waves meet, they are what? They're initially in phase, but then they travel 2 different distances. One travels 2 meters, and then the other travels 3 meters. So you can imagine they start right here. One travels to this point, and then the other travels a longer distance to that point. What happens to them? All right, I'm going to stop. I'm going to stop at 108. Okay, let's see. C is right. Awesome, that's great. Listen, what's going to happen here? Let me go back up so we can. You're going to have two waves that'll travel. So I'll draw the first wave, right? It has a wavelength equal to 1 meter. That's the wavelength, 1 meter. And the other wave, and so this wave, let's say, travels 3 meters. There's 1 wavelength, 2 wavelengths, 3 wavelengths. So that wave travels 3 meters, which is 3 wavelengths. Now you imagine the second wave actually only travels 2 meters. Oh, shoot. So this wave is only going to travel 1 wavelength, 2 wavelengths. And so when these two waves come together, they're going to come together right here. They're going to be in phase. They're going to be shifted by 1 wavelength, but that still is in phase. It's as we say, 360 degrees out of phase. But you'll still get total constructive interference. Okay, because your peaks align with your peaks and your troughs align with your troughs. This is going to be the underlying principle between the double slit diffraction, and single slit diffraction and diffraction gratings all in all. So we'll see this idea a lot in the next couple of days. All right, we'll come back to this after we do double slit. We had left off with a question though, which is similar to the one that we just did. Here we have waves from a radio station. They have a wavelength of 600 meters, and they arrive at a home receiver a distance of 50,000 meters away by 2 paths. One of our waves, they both start here. They're both in phase, and we would say that they're coherent, so that their phase changes at the same rate. This first one goes and it bounces off of this mountain and comes to your home, and then the second one goes straight to the home. And then when you have these two waves come together here, we want to know what happens to them at that point. Or rather, I'm sorry, there is a distance, rather, where you can get destructive interference, where these two waves, when they meet at this point, they will have there'll be no signal at all. So when they meet at that point, they'll look like this. So that when they add up, you get nothing at all. So we want to know what is this distance, I'll call it x, so that you get total destructive interference when these two signals line up. Oh yeah, where are they? Oh, it's on the next page, isn't it? What are they? 300 and 600. I'll write them in. B is 300, D is 600. Okay, y'all doing pretty well actually on this. So by how much do they have to be offset in order to get destructive interference? One of them has to be offset by what amount in order to have destructive interference? How much of a wavelength? A full wavelength, a half wavelength, a quarter wavelength. In order to get destructive interference, by how much do they have to be offset? A half a wavelength, right. So in this case, our wavelength was like 600 meters, right? The radio is a really long wavelength radio wave, 600 meters. So that means that it's going to have to be offset by 300 meters. We'll stop in about 10 seconds. stop at 3:15. Okay, good. A lot of you put B actually after I said 300 because you were thinking, well, gosh, in order for these two waves to be offset by 300 meters, then the path length difference between the two waves has to be 300 meters, right? But notice that when our wave travels here, this extra wave travels a distance here, and then it travels that same distance again. So this black wave, it has to travel an extra distance of 300 meters so that it gets to be offset from the first wave by 300 meters. But in order to travel an extra distance of 300 meters, it just goes 150 meters and then 150 meters again. So 150 is the right answer here. A is correct. Don't worry, we're going to see this again with double slit diffraction, and that's really where this comes into play when we look at how waves interfere with one another. I think that's the very next one. Okay, so most light sources, what does it mean to be coherent? For a light source to be coherent, what does that mean exactly? It has to do with the phase, right? For the coherence of light. Right, if I have two light sources that are coherent, it doesn't necessarily mean that the light sources don't change phase. Like a light source that changes phase, the peaks and troughs of the wave would move back and forth like this. You're getting very sleepy. Oh, you're already very sleepy, aren't you? Okay. All right, so anyway, for two light waves that are coherent, that means that they're going to change their phase at the same rate and in the same way. So, like for example, all these light bulbs that put off light, they're all changing phase, but they're all changing phase in different ways because the light is originating from different sources. Similarly, light that comes from the sun is changing phase like crazy because it's a result of all these different things traveling through space and in the sun and going through the atmosphere. It alters the phase of the light wave. All right, but one way to get light that is coherent, one is to use a laser. That's the really great thing about lasers, is that they can be made coherent so that they change phase at a very constant rate, or they don't change phase at all. Another way, Young did this, Thomas Young did this back, I don't know, 150 years ago or whatever. They didn't have lasers back then because they weren't invented until, gosh, mid-1900s or so. So the way he did this is that he would set up a set slits so that he would have a lamp right here. It would shine light onto the first slit, and it would create a little pinpoint of light. Now this light does change phase. The peaks and the troughs of this wave are moving back and forth in space. All right, but because I just have a single point, I have a single source of light, and it further goes on to these two additional slits. It's like each of these slits is an exact copy of this first source of light. So I get two sources of light that are changing phase, but they're changing phase in the same way. Okay? So then we have two coherent sources of light. So make sure that you understand coherence. You'll probably see a question about, what does coherent mean? How can we produce coherent light? All right. Thomas Young did this experiment. It was pretty groundbreaking at the time. It's still groundbreaking. It's a pretty big deal. Called the double slit experiment. It was in 1801. And if you recall from chapter 6 or whatever, we talked about the history of light. What did this experiment show that light was? A wave or a particle? A wave, right. And that held for like 100 years. People said light is a wave. For 100 years, people said that. So it demonstrated very effectively that light is a wave. And what he did is he had these two slits. Right? He had these two slits, and they were each producing light. And what he showed is that when you put a screen, this is just a screen right here. When you put a screen behind this source of 2 points of light that are coherent and have the same wavelength, then you'll see not 2 points of light, which is what everybody thought at the time. Right? Everybody thought, well, gosh, you're going to see a point of light right here, and you're going to see a point of light right here, and that's all you'll see. What he saw instead was that he had a really bright spot right in the middle. So he had a really, really bright spot right in the middle, and then he had dark spots flanked on either side. Now, often we're going to draw a graph to demonstrate this. So let me draw it first, and I'll show you. Ah, shoot, I need to redraw it. There we go, that's pretty good. So we're going to draw a graph here where these peaks represent the bright spots. That's where the two waves come together and they constructively interfere. So at these points, when I get waves that come together, what I'm dealing with are two waves that look like this. On the other hand, when I have destructive interference, what I'm dealing with are two waves that look like this. All right? For waves to destructively interfere, their waves have to be offset by what amount? For destructive interference, how do we get 180 or a half a wavelength? Right, so their distance, or the amount of separation, the amount of, the path length difference, the difference in the path that they travel will be offset by a half a wavelength. Or we'll see by 3 halves wavelengths or 5 halves wavelengths, and on and on. For in order to get constructive interference, like here, and here, and here, and here, our waves are going to have to be offset either not at all or by a full wavelength, or 2 wavelengths, or 3 wavelengths, and on and on. This graph right here, this just represents the intensity of the light. So here, this is really bright, this is really dark. Really bright, really dark, really bright, really dark. Okay, so the derivation for this is pretty simple, so we're going to go through it. It's not, I want to show you the geometry, and you might be asked something about this on the test as well. For constructive interference to occur, the two waves must be in phase. For the central maximum, that is the part that occurs right here in the middle, that brightest spot in the middle. For the central maximum, the difference in the distance the rays travel is 0. So total constructive interference occurs. Interference occurs. All right, imagine I have two sources of light here and here. One of them travels this distance, and one of them travels this distance. But because these are the hypotenuses for the same triangle, that's going to be the same distance. So this ray and this ray will travel the same distance to the central maximum. So the path length difference, I'll call it PD, the path length difference for these is equal to 0. Now, on the other hand, if I have a ray that travels from here up to here, and from here to here, this little bit right here, which I show you right down here, is the path length difference. So here, my path length difference is given by that, and that path length difference is equal to d sine theta, where d is the distance between the slits, and theta is the angle here between these 2 points and where our first maximum occurs. So this is our path length difference is given by d sine theta. What must that be equal to in order for us to get our first maximum? What value must it be equal to? Well, let's do it as a clicker question. So what must the path length difference be at this point in order for us to get the first maximum? Is it 0 wavelengths, a quarter wavelength, a half wavelength, or 1 wavelength? At the first maximum, right here, our path length difference is equal to d sine theta. What must that be equal to, A, B, C, or D, in order for us to get constructive interference at our first maximum? What must the path length difference be? By how much must the waves be offset in order to get constructive interference? Feel free to ask your neighbor. More of you have it right than wrong, but it's still quite a few of you have it wrong. All right, I'm going to stop at 1 minute. Okay, good. D is the right answer. 1 wavelength. The difference must be 1 wavelength. This little distance must be 1 wavelength in order for us to get constructive interference over here. Because when I have 1 wavelength offset, I have these 2 waves, they come together when they're offset by 1 wavelength, I still get constructive interference. What is it here? If I have a point here, what is my path length difference? It's a half a wavelength, right. So here I have 0 wavelengths, here I have a half a wavelength, here I'll have a full wavelength, here I'll have 3 halves of a wavelength, 2 wavelengths, and I go on and on like that. Okay, so let's sort of formalize this. So the first bright spot occurs when the 2 waves are offset by 1 wavelength, and the path length difference is d sine theta. Right, we just determined this from geometry. We determined this from what we know about waves and how they get to be either in phase or out of phase. And we can set those 2 equal. So the position of the bright spots then is going to be equal to some integer times lambda. And m here is going to be 0, 1, 2, 3, and on and on. It doesn't go on forever, but it'll go on for several orders. These are called orders. And it's an integer value. I'm going to draw the interference pattern over here. It looks something like this. A bright spot followed by dark spots, followed by bright but dimmer spots. So we call this our 0th order. That refers to this value. We call this our 1st order, our 2nd order, and on and on. It's symmetrical, so we get over here our 1st order, our 2nd order, and on and on. Okay? Again, it doesn't go on forever. It will stop eventually, and we'll talk about that later when we get to diffraction gradients. So we have a similar expression for destructive interference. Here the path length difference has to be half a wavelength offset. So d sine theta, that gives our path length difference. That's the difference in the distance that the 2 waves travel, is going to be equal to m plus 1/2 times our wavelength. All right, so we're using the same order numbers here. Except now we'll have 0 plus 1/2, we'll have 1 plus 1/2, 2 plus 1/2, and on and on. Okay, so you'll add the order number, m, of the bright spot that is adjacent to the dark spot. So here will be a 1/2 a wavelength, 3 halves wavelengths, 5 halves wavelength, and on until the interference pattern stops. Okay, these are on your equation sheet. I think. Let's double check that. Yeah, it's right up here. All right, but you'll need to recognize that those are for double slit. We're going to have similar expressions for a single slit interference, but it's a little bit different. And then we'll also have a similar expression, or an identical expression actually, for the diffraction grating. Okay, so as always, you just need to know what's on the equation sheet and know what they mean. Okay, another thing that you'll need to do is to find the distance between the central maximum and the bright or the dark spot. And that's equal to L tan theta. Let me show you. So here's our interference pattern. Here's our double slit. The distance here between the double slit and the screen we will call L. This distance, y'all remember what we call this distance? This distance was D, as in D sine theta equals m lambda. So that distance is D. The distance, let's say I want to know the distance between the first order fringe, or the 0th order, and the first order. Say I want to know this distance, then I would say this is equal to y. And that's the y that's referred to here. The angle theta, I'll draw an axis here. The angle theta is this angle. We're approximating because we actually have 2 rays that come here, that come up to this point. Right, the 2 slits are so close together that the angle, those 2 different angles are basically the same. You follow what I'm saying? I actually have 2 rays that are coming up to this point, but the angle for those 2 rays we can approximate to be equal to this angle. Because these slits are so close together, it's as if they're coming from the same point. Okay? We'll work through some problems with this, but just keep in your mind straight what all these variables are. Notice this really just comes from our understanding of our right angle triangles, because this distance is L, this distance is Y. If I want to know Y, it's just going to be L times the tan of theta. Because tangent of theta is what? SOHCAHTOA, opposite over adjacent. Okay? You with me, folks? I was telling my wife the other day that my physics teacher in high school, who we love, right? Like, she was Helen Perry. She passed away, but she was like the most awesome lady we ever met. She made everybody just really love physics. And she, well, maybe not everybody, but some of us she made love physics. But she used to call us dum-dums. And I was thinking, is that appropriate? Like, what if I were to call y'all dum-dums? How would you feel? Probably like you're in 3rd grade or something, right? But my wife said that you should never call a student dum-dum. But I told her it's like a term of endearment. Did any of your professors ever call you dum-dums? You have a professor that calls you that?
No, school art physics teacher would call us dum-dums all the time.
Was it Helen Perry? I'm not going to start calling you dum-dums. Because you're not dum-dums anyway. So, all right. Let's try this. This is a good test question. Don't forget, you're going to see things not in SI units. Don't forget, nano is -9, milli is -3, 10 to the -3. That's just the way we measure those things. So nano is -9, milli is -3. If y'all can maybe remind me at 11:32 to start handing out your exams. Milli is -3. And nano is -9. So like this is 500 times 10 to the -9. And this is 0.4 times 10 to the -3 meters. Couple steps to take here. First, you need to figure out what is theta for the first order, and then you need to determine the distance between the 0th order and the first fringe. All right, we'll do about 15 more seconds. Just guess if you're not sure. 10 seconds. 2:45. Stopping. Going to do the next one if you're waiting. Okay, let's see. I think A is right. I'm going to go and mark it correct. So here we say d sine theta equals m lambda. D is 0.4 times 10 to the -3 sine of theta. Then I need to figure out what is my order number. I like to draw a picture just to remind me. I'm looking for the distance between this fringe and this fringe, between 0 and 1. So that means my order number here is going to be 1. All right, so I have d sine theta equals 1 times our wavelength, which is 500 times 10 to the -9 meters. And then I solve this for theta. I divide both sides by that d, and then I do the inverse sign, and I get theta is equal to, and then what is theta? I know some of you have it. What is theta? What is theta? Come on, what is theta? Somebody. Do I have it? 0.072. Is that right? Is that right? Y'all agree? Okay, Ashley, I like that. All right, so check your calculator. I know some of you are in calculus. They might put you in radian mode. So make sure on this test, we'll never be in radian mode. All right, so just make sure you check your calculator before you take the test. When I was in college, I put a little note up at the top of my calculator. It said, check mode, because I had to switch back and forth, radian to degree mode. So make sure you don't miss a question because of that. And then we say y is equal to L tan theta. And we solve for y. Y is, L is 5 meters. That's the distance away from the screen. And tangent of 0.072. And what do we get there? We get 0.00625, is that right? Okay, and that is 6.25 millimeters. Listen, you're going to have a question like this, no doubt. Just you'll have a double slit, and I'll ask you something like that. Probably this: what is the distance between the fringes? Or I could give you the distance and ask you what is the order or something along those lines, solving for one of these. But make sure you go through this. There's some homework questions. If you look at all the old tests, you'll see questions like this on all of them. Let's do this last question, then I'll hand back your test. What is the path length difference of the two waves that create this dark fringe in this interference pattern? All right, let's see, it's stop in about 10 seconds. Stop at 45. Okay, awesome. B is right. It's offset by a half wavelength. Remember, 0 wavelengths, half wavelength, 1 wavelength, 3 halves, 2 wavelengths, 5 halves, wavelength, and on and on. Those are our order numbers of our fringes, or our bright and dark spots. Oh, let's see. Y'all don't have any over 90%, huh? Do you have any jokes today? I should, because it's a rainy day. So, where does bad light end up? In a prism. Okay, listen, I'm going to hand back your test. Once you get it, you can go. I'll lay them on the floor. All right, Kyle. Malcolm. Caleb Jackson. Devin Brown.